Hi, in this video, we are going to discuss about three-phase AC circuits. So before getting into the concepts of three-phase AC circuits, let us know the advantage of three-phase system over single phase and what is the necessity of three-phase system. So first, the necessity. We will discuss about the necessity of a three-phase system. So if you want to talk about the necessity of three phase, there are certain loads which require only three phase. So loads, okay, requires only three phase. So most of the industries, okay, what the machines we used in the industries, so they run on three phase, so on a polyphase supply. So polyphase refers here more than two phase, that is greater than two phase, greater than or equal to two phase or greater than two phase, we refer that as a polyphase system. So the second necessity is in practice, okay, three-phase system is found to be more economical. So rather than single phase, three-phase is more economical. So it has certain advantages over other polyphase system. So if you take four phase, okay, four phase means it is three wire and one neutral, okay, refers to four. So in that case it has more advantages, when we talk about three phase over other polyphase system. Hence three phase system is very much necessary, and it is required. Many loads are operating using three phase supply. So now coming to the advantages of three-phase system. If you want to come to the advantages of three-phase system, there are many advantages, out of which I will be listing only the few advantages here. First advantages is the output of three-phase machine is always greater than single phase. So if you say output is of three phase, output of three phase is greater than single phase. Okay. If you want to talk in terms of greater than single phase means how much. So if you say how much means the output is 1.5 times greater than single phase for the same rating of the machine. Okay, for the same rating of a machine, okay, same size or same rating, approximately it is 1.5 times greater than single phase. The second advantage is for a given size of a machine on a voltage, okay, for a given size and voltage, a three-phase alternator or three-phase AC generator occupies less space, okay, less space, okay, and less cost, okay, less cost. Advantages over single phase, you can say. So less space and less cost comparatively to single phase. And the third advantage is the voltage regulation is better than voltage regulation is better, okay, is better, so comparatively with that of single phase. So these are the advantages of three phase over single phase. The next advantages is the fourth one. The fourth advantages is it is possible to produce rotating magnetic field with stationary coils by three-phase system. So with rotating magnetic field, so it is possible to produce rotating magnetic field with the stationary coils by using three-phase system without moving the coils, rotating the conductors. We can have a magnetic field, okay, using three-phase system. Next, the fifth point is single phase can be obtained from three phase. Single phase can be obtained from three phase, okay, from three phase. But vice versa, it is not possible. Vice versa, not possible. Not possible. That means three phase cannot be obtained from single phase. So single phase you can obtain from three phase, but three phase you cannot obtain from a single phase. So the next advantage, I can say the sixth advantage, power factor of single phase, okay, power factor of single phase is poor, okay, than three phase. That means three phase power factor is better than single phase, and which is very important in power system network, that we should have a very good power factor, which we have discussed in single phase. So when we have so many advantages over single phase, so we prefer always the three phase system than the single phase. Now coming to the generation now. Generation of three phase voltages. If you observe, this is the now if you observe the generation of three phase voltages here, let us assume this is a three phase system. So the conductor now, this is a conductor. When you rotate a conductor, so we have here three conductors, okay. In the three phase system, we have, let us assume three conductors we have, that is one R, Y, and B. Okay, instead of differentiating with actual colors, we differentiate this in three colors. That is one each phase represents three colors here. So in the three phase system, if you observe here, there are three equal voltages of the same frequency but displaced from one another by 120 degree. So this I would be explaining by drawing the phasor. So when you observe, these conductors are rotating, okay, and it cuts the magnetic field. So we have the voltage produced here. So voltage produced, so observe this voltage is produced at a particular point. The other voltage is having, after a certain phase shift, the other voltage is starting, and after certain phase shift the third voltage is starting. So but they have equal in magnitude, okay, they have equal in magnitude. So let me write this with the so there are three voltages. Let us say one of the voltage reference, let us say this as ER. Okay, so this is nothing but ER reference, and one of the voltage is now EY, and this voltage as EP. So R by B, if you take anti-clockwise rotation, the displacement of this will be 120 degree. Okay, so there is a phase shift of 120 degree. So if you take ER as a reference, so EY, if you take in anti-clockwise, EY is lagging, okay, EY is lagging ER by 120 degree, and EB is lagging ER by 240 degree. So when you want to write a reference, suppose ER is written as magnitude EM at an angle 0. Okay, so this is how we write, or this can be written as instead of like we have normally seen in the single phase, like we have V is equal to Vm sine omega t. In the same notation, if you write instead of the voltage in one of the phase is ER is equal to Em sine omega t. If you take ER as a reference, because omega t is normal with respect to this. So now EY is lagging ER by 120 degrees. So EY can be written as EY is equal to EM sine omega t minus 120 with reference to ER. Okay. So next we have EZ. Next we have EZ. So EZ can be written as EM sine of omega t minus 240. That is with reference to ER. So let the three coils be rotating in the anti-clockwise. Considering that, okay, we write the voltage equation as this way. The equation for the induced voltages in a three-phase system. Now, how this EMF are induced? So we know when a conductor is rotated in a magnetic field, it cuts the flux and EMF is induced. So let us take three conductors, for example. So let us take three conductors. Let us assume there is a pole. Okay. Let us assume there is a pole, and let us say this is North Pole and South Pole, and we have a field here. So let me indicate with different color the field in yellow. So the field is always from north to south pole. We know that. So let me not, indicate the direction. So let me write the conductor now. Conductor, one of the conductors. So let me write it in the same color, R, Y, B. So let us say R is here. So next is Y. So I'll use little darker color. So phase shift is around 120 degree. Y and B. Okay. So if you observe this, let me indicate the one. So let me indicate this as R1, R2, and this one as Y2, Y1, and this one as Z1 and Z. So if you observe this conductors, so the EMF induced in, okay, so let me use the same colors now to denote this. Okay, this refers, suppose taking reference ER1 R2. Okay, that is induced in the conductor ER1 R2. The other EMF induced, okay, in case of other one of same magnitude. So let me say this one as E Y1 Y2, and the third conductor induces EMF. Let me take B. So B at 240 degree. So it starts from here. Okay. So it goes like this. So this one is E P1, sorry, E This, let me call this as V1, V2. Okay, so this becomes EB1, B2. So we have three phases R, Y, B. So the three conductors rotated in a magnetic field. So when it cuts the magnetic field, okay, when you rotate these conductors, when it cuts the magnetic field, the EMF induced, we called ERR1, R1, R2 in case of the one of the phase of the conductors, let me say red, and EY1, Y2 is the EMF induced in another conductor, say Y1, Y2, and B1, B2 is the EMF induced in another conductor, that is B1, B2. So these are the three EMF induced. If you observe, they are unequal in magnitude. As I said in the previous case, if I refer ER, capital R, so R refers here the red phase, that is R1, R2 conductor. You know, the ends of the conductors is mentioned as R1, R2. So ER can be written as EM sine omega t, correct? Because it's a sinusoidal wave. The other one, E y, okay, induced in the conductor Y1, Y2. So let me say this as EY. EY is equal to EM sine of omega t minus 120 because it is in the anticlockwise. So if you refer this, it is having a phase shift of 120 degree here. Okay, the other blue has a phase shift of 240 degree. It is only starting after 240 degree, so that is, we call it as EB is equal to EM sine of omega t minus 240. So these are the three voltage equation EMF induced in a three-phase system. So this is how the EMF is generated when you rotate a conductor in a magnetic field. Okay, so now we shall move on to the next topic, that is star connected system. So let us move on to the star connected system in the next video. Thank you for watching this.